Hello everyone and welcome to this next lecture on Python Power Electronics, and with this lecture I'll be starting the video lecture series on operation and control of a UPS, that is an uninterruptible power supply. So as always, let me go over to my own site, Python Power Electronics. Just Google it and the first link is my site. So to begin with, this is a tutorial. So go over to the tutorials page and you'll see this new link coming up, operation control of a UPS. You can click in this and you see here this is what it's about. So basically it just says that this is a tutorial of a UPS and it takes you step by step through the entire concept. So there are several resources. There is going to be a YouTube video lecture series, which is this one, so I'm not going to open it again. There are simulation files that you can download from Gumroad. So this is a simulation file. This is an entire package. You can just take this if you're interested in continuing with this. And of course these are the help links, how to install, how to use, any updates, things like that. So to start off with, I am going to go over, I already have this simulation package. Now what I will do, let me start off with my circuit simulator. So first I go into the virtual environment directory. This is where it is. I will first enable my virtual environment, which in this case is Python 3. So this is a continuation of the previous lecture where I installed the latest version with respect to Python 3. And now so once I'm in this, I have already done the make migration and the migrate, and I've also copied the simulation collection from the previous simulation, which was Python 2, and it'll work, no problem. So all I have to do is launch the circuit simulator. So the simulator is working, that's what it shows. There are no issues. All I have to do, go over to my Google Chrome, and my simulation library shows the one simulation which I did before in the previous lecture. That is, this video lecture, this example was only to show you how to simulate a circuit. That's it. Now coming to this topic of what is exactly in this package. Now if you go to that Gumroad link and you download the simulation package, you will get the zip file. Alright, I already have it here, so let me extract it. This is what it is. Now there are several folders. Alright, there are 6 folders altogether, and we are going to go progressively one by one. So the final simulation is this one, closed loop voltage control. This has the entire simulation code for the entire closed loop control of a UPS system. Alright, but what I'm going to do is I'm going to start off from the very basic. Alright, I'm going to start off with PWM concept. I'm going to talk about how you can filter this PWM concept to get a sinusoidal waveform, and then how you can use a 3-phase voltage to get a switched waveform, and how you filter that to get a smooth sinusoidal 3-phase voltage waveform. Now these are all open loop, which means the next step is the current control. So this simulation will tell you how you can control this inverter such that the output currents are regulated. But now this is a UPS, that's not what we want. We want to regulate the voltages. So that's where this final simulation comes. This will tell you how to regulate the voltages as well. So this is how I'm going to progress. Now let's go check this out. Now in this also I have broken it up into 2 parts, simulation, that is square wave and pulse width. So let's start with square wave. Now there is only one file which is a circuit file, that is inverter leg. Right, let me open this. Alright, so if you see, this is a very simple circuit. It has only one one leg of the inverter. So basically there are two switches with their anti-parallel diodes. So there's a switch and a diode parallel across it. There are two voltage sources. There is actually one voltage source, but this is split into two with a midpoint. The midpoint of the voltage sources is connected to the midpoint of the switches. So this is how the circuit closes. All right, we are measuring the two voltages, and finally we are measuring the voltage at the output of the switch. All right, that is the midpoint of the switch. The reason is simple. What we are trying to do is, what I want to show you is, how does a power electronic circuit even produce an AC voltage? That's the first question, right? Now, we all know that our regular supply is a sinusoidal voltage, or at least close to sinusoidal. You don't actually get perfect sinusoidal nowadays. There are harmonics, but ideally it should be a sinusoid. Now, this sinusoid is produced with a generator, a synchronous generator, which is usually either a nuclear power plant, or it could be a thermal coal, steam, or it could be a hydroelectric. So this is usually a generator where there is a prime mover moving in a magnetic field, and therefore it produces therefore that mechanical energy is converted to electrical energy, and finally you get a sinusoidal output. Now, in a power electronic circuit, you don't have a moving part. There is no moving part. It's a static circuit. Nothing moves. Now the question is, when nothing moves, how do you still generate an AC voltage? All right, and that's what I'm going to show you gradually. So this circuit is basically to show you how you can switch a power electronic circuit to produce something close to an AC voltage. All right, so let me now go over to my atom and also add over the entire project path. So go to the virtual environment and let me add this entire project. So the first step is we are looking at PWM concept. So let me open PWM concept and let me expand square wave. So there are a few control files. There is one control file, squarewave.py. Let me open that. And this squarewave.py is basically just going to produce a switched waveform according to an AC signal. So I have an AC signal, and I'm going to just turn on the upper switch. I'm going to turn on the upper switch in the positive half cycle of the sinusoid of the reference sinusoid, and I'm going to turn on the lower switch in the lower half cycle of the sinusoid. All right. So what I will get is a switched square waveform. All right. Now the question is, what exactly is the use of a switched square waveform when what we want is a sinusoid? And that's where this Fourier analysis comes in. Now I have included this file to show you that inside a square wave, that is according to Fourier series, you can decompose any periodic waveform into a series of sinusoidal waveforms. All right, and this is what this file does. It is going to decompose the square waveform, because it is a periodic waveform. It's going to decompose it, or rather rectangular waveform, into a series of sine waves, and it is going to show you that there is therefore a fundamental component of a sinusoidal waveform embedded inside this, and this is what I will show you, and these are the outputs finally. So let's go over and let me start the simulation. So I'm going to create a new simulation. So let me call this, let's call this single UPS. Okay, I have several, and square wave modulation, okay, because I'm using a square wave. So I'm just actually, you can write any description you want. I will just copy it here. You can write a detailed description if you want, and all these can be the same. These, I don't think you need to change this. For the directory, I'll just go over to the directory, do a right click, properties, and I will copy over this path. So I copied the path and I saved it, and there are no errors, so it's okay, everything's running. So now that this is done, let me start adding some circuits. So as you see, now this is another aspect which I don't know if you've noticed it, but in this latest version of the circuit simulator that I've released, I have done a little bit of a makeover of the visual aspect of this, so it looks a little cleaner than it before, right? The fonts are a little better, the buttons are a little better. Anyway, it's just in case you found it ugly before, you might like this a little better. So I'll just go over to my virtual environment, single UPS, PWM concept, square wave, inverter leg, and I can just call this single inverter leg. So it's just one leg of the inverter with an upper switch and a lower switch, and the midpoint is taken out. So let me save this. Okay, there is no error. Now in this case, this is the only circuit which is there, so I don't need to add any more. So let me just go back and let me process this. As I said before, always when you add, after you've done adding the circuit, or even if you change it, you must click process circuit schematics. Now here you see the message, the circuit does not have any detectable errors, so we are okay, at least for now. We don't have to add anything more, so we can just go back to the main page. So let's go to edit circuit schematics. Now it already lists this file, so we can view the components and it lists this. Now before, you would have to actually manually change each and every parameter. All right, you'll have to edit this, you'll have to change it maybe to whatever, let's say 600, okay, and you'll have to save it, and you'll have to do this for every component. Now in the latest version of the circuit simulator, I have created this separate file. You can upload a parameter file. All right, this has to be a parameter file. You can't upload just any file. It has to be a parameter file. It has to be a .csv file. You can upload it, and when you upload it, it will extract all the parameters from that and will put it into the database. So let's go back and check if there is one, and there is one underscore params file. Let me open this and check it out. So you see, I have provided this sample case. If you download this example, you will see there is a sample case where I have provided all the parameters of this inverter leg of this particular circuit. So I'll just close this, and what I'm going to do is I'm going to upload this file. So I'm going to choose file, inverter leg underscore parameters. Okay, so it's here listed here, and you just have to click upload. And you see all the parameters have changed. So it can directly extract all the parameters from a parameter spreadsheet and insert it into the database, and now it is ready for a simulation. Similarly, if you do change anything here and you want to back it up, you can click on export parameters, and it will back up, it will write all the parameters of the circuit simulator of all the components in that particular circuit into a CSV file with the name appended with underscore parameters, right? So if this was x.csv, the file will be called x underscore params.csv. All right, so this is a good way to exchange your information and collaborate. So if you want to like give your files to somebody else, you can just export parameters all over the place and just zip the file, zip the entire directory and send it over. So anyway, this is done. Let's go back and check on this. Now that this is done, let's go over to control file. Now we have two control files. All right, the first one is square wave, the second one is Fourier analysis. So let's add both of them. So first one, square wave.py, and let's call this square wave modulation. You can write whatever you want, no problem. And let's add the other one also, Fourier analysis, and let's say Fourier analysis. Let me save this. So now I have to. So now the next step, of course, I have to configure them. So now there is nothing in this file. As before, in the previous sections, you would have to actually manually add each and everything. And as before, now there is the new option. If you have a descriptor spreadsheet, all right, like this one, let's call Fourier analysis, and let's call this descriptor. If there is a descriptor spreadsheet, and this descriptor spreadsheet is there in this simulation package. So if you download this, from Gumroad, you will get this entire simulation package. This is the descriptor for that particular control file, Fourier analysis. So this tells you all the inputs, outputs, static variables, variable storage elements, everything. I am going to upload this file, and I'll tell you what happens. So you just have to choose this and click upload. And you see it has already populated the entire database. So this way this simplifies your problems in a big way. You do not have to actually manually change everything. You can just, if you have the simulation package, you can just click on the upload files and automatically populate the database. So let me go back and let me do this also for square wave. So we have square wave underscore desk, upload the file, and we are now ready. You see, both the simulations are ready, both the control files are ready, our parameters are ready, our circuits are ready. We are now ready to go. All we have to do now is go to the view output and click on run. So let me click run, and always when you click run, always go to the terminal and check if there is an error, because sometimes there are errors which don't show up here. So anyway, now that we are done, let me go and see what I want to look at. The most important thing will be, of course, the output voltage, because that is the output of the circuit. So let's see what this voltmeter out value is, and what we actually get out of it. So let me add a plot. Let me call this plot output voltage. Fair enough. Start the voltage. So you see plot title. Now what will I add? I will add voltmeter Vout. So let me add this, and let's call this VO. Let's save this waveform. Now, do we need to add anything else? I don't think so. This should be enough. So let me call this done. So now we have the first plot. So let's look at what it is. Let's plot this file. Let's click on plot. It seems to have plotted something. Let me go over to the directory. And yeah, this is running. I mean, it's just started. So let's give it a little try. All right. So now that the simulation should have progressed a little, let me now plot it again. And as you can see, this is the output voltage. So first and foremost, we are using two supplies of 100 volt each, and that's why we're getting a 100 volt peak. Right? If you want to verify that, let's do that. Let's verify that also, no problem. What's this one? Let's add another plot, and let's call this input DC. And yeah, we can just take any one of them. Let's just take VDC upper, and we'll call this VDC1. They are both the same, so you don't have to really plot both of them. So I'll just be done with this, and let's plot this voltage. So actually this is a weird way of actually showing it, but this is how the calculation is. So you see it shows a square wave. It's not really a square wave. It says 0 plus 9.99 e to the power 1. So it's actually 0 plus 99.99. So it's actually 100. All right. So I don't know why it does this, but this is how Python sort of interprets numbers which may not be exactly 100. So it's actually 100 volts. And coming back to this topic, to this plot, you will see this is a rectangular waveform of 100 volts. The on time is equal to the off time. The on peak is equal to the off peak. And therefore, this is a periodic waveform. And as I said before, when you have a periodic waveform, you can use Fourier series to decompose this into a series of sinusoidal waveforms. Now let me show you what that is. Now, in this file, which is Fourier compose, there are a number of variables, and these are all variables which you can plot. So Fourier funda. Fourier funda basically means is the fundamental component. Then there is a third harmonic, fifth harmonic, seventh harmonic. So let's have a look at this and find out what these are. And just for your information, if you go up, I am calculating 15 components. So there's DC all the way up to frequency number 14. So it's the 14th harmonic. All right. I'm also calculating the DC component. So let's go and plot these and let's see what happens. Let's add this plot and let's call this Fourier components. Let's call this start. So let's plot those values. So first Fourier funda, and let me call this B1 because this is the fundamental component. Let me also then plot third component B3. Let me plot fifth component B5 and the seventh component, sorry, wrong, B7, same waveform. So now that we're done with this, let's click done and let's plot this. And you see what this is. This shows you all the components. The blue is the fundamental. Now this is still not the best plot, and the reason is I don't know where the output is. So let's plot another one where I superimpose just the output voltage with the fundamental. Let me add another plot and say compare component or compare fundamental. Let's start this plot. So let's plot the output voltage. Let's call this VO, V0, VO. Save this waveform. Let me then plot funda. And let me call this V1. So now let's compare these two. Let's be done. And let's go down and plot this. So we have this, and as you can see, this is a very nice description of what's happening. You see here, the output voltage is periodic, and you see the Fourier component is exactly aligned with that. All right, is exactly aligned, and this is how we are able to achieve. We don't have a synchronous generator. All we have are two switches, but even with those switches, we are able to achieve a rectangular waveform, and we are able to show that using Fourier series, this rectangular waveform being a periodic waveform has this fundamental component. All right. Now this fundamental component is actually bigger, and the reason for that is simple. There are other components. Simple is like, for example, if you look at this, you see there are other components which are superimposed. So you might ask, what is the relationship between all these? The relationship between all these is, if you take a sum of all the components, they will begin to converge to the actual waveform. All right. Now let's do that. I also have that plotted out. For example, if you go to the control file and you see this Fourier sum, Fourier sum does exactly that. It sums up all your components. So let's look at what the sum of all these components is. Let me add a plot. Again, let me just say compare. Let me say compare Fourier this time, because I want to compare the Fourier output. As before, let's plot the output voltage. Again, it's 0. Same waveform. Let's go to Fourier sum. All right, and let's call this V sum. Save this waveform. I think that's all we need. You can just click done, and here again you can have as many plots as you want. So I would strongly recommend you to just play around, plot all the values, check out everything. Just feel free to play around with it, and if you can break it, go ahead and break it. Just tell me what it is and I'll figure out the debug message. So let's plot this. and check it out. So now you see what's happening here. This shows you exactly how Fourier works. We have summed up 15 Fourier components. These are 15 harmonic components, starting from the 0 DC component, fundamental, second harmonic, third harmonic, all the way up to 14th harmonic. We are summing up 14 harmonics in this manner. And when you sum up 14 harmonics, this is the sum that you get. Alright? Now, again, I would strongly recommend you to go back and play around with this value. Alright? What happens if you decrease this to 5? Or what happens if you increase this to 150? What happens then? Because now, as you increase this number, and I'm not going to do this, but you can try it out. As you increase this number, this waveform, that is a sum, will start converging towards this square. And this convergence, there's a lot of theory behind it and a lot of work done, so I won't talk about it here. But this convergence, exact convergence, will happen almost near infinity. So you need a ridiculously large number of harmonics to be able to get a square wave. Alright, so by all means please try it out, because this is a very good idea of how simulation works, of how square wave works, how Fourier works, what is the idea behind having a square waveform. Now, since this is mainly a lecture on power electronics, let me talk a little about the concept of power electronics. So let's talk about this. So this is the Fourier components. Now we have generated a fundamental. So that's great. We have a fundamental because that's what we want. We want the 60 Hertz. If it's US, Canada is 60 Hertz. The rest of the world is typically 50 Hertz. But the most important, we have a fundamental component. This fundamental component is the main workhorse. Alright. So if you want to supply it to a motor, if you want to supply it to anything, it is this fundamental component that is what is going to do the massive amount of work. These harmonics are totally unintentional. We don't want these harmonics. We want this fundamental. But these harmonics appear. Why? Because Fourier series, when you have a periodic waveform and something like a square waveform, these are all the components that make up that square waveform. That's all. That's simple mathematics. But now what happens to these harmonics? We don't want this. And this is the problem with this strategy of modulation. This strategy of modulation was popular for a long time. Why? Because it doesn't take much to use this, to implement this rather. You can implement this with simple analog circuits. Very simple. You don't need a chip, you just need an op-amp. You don't need an op-amp, you need an oscillator, you need an op-amp, and you're done. But the problem is, how do we get rid of these harmonics? The third harmonic, fifth, the biggest are the worst are these lower frequency harmonics, alright? Because these lower frequency harmonics can cause heating in machines, they can cause all kinds of problems, they could even damage them because you have more vibrations. Now, to eliminate this is a challenge, and in the later lectures I'm going to show you how we can filter this, or rather how it is tough to filter it. Alright, so I think with this I'm done with this lecture series, and in the next lecture series I'm going to talk about how pulse width modulation can remove these frequencies and produces a much more cleaner output. So with this I'm going to wind up this lecture. Thank you so much for watching, and if you have any doubts, message me on Facebook or email me. If not, just wait for the next lecture series to come out. And thank you again. See you soon. Bye for now.